Hi and welcome to this third video in the Vectors and Lines series of videos. This is Specialist Maths in Queensland, Unit 3, Topic 2, and this is video 3. So here's a couple of extra ideas. We're going to talk a bit about parallel and perpendicular lines in terms of vectors. So two lines are represented as L1, L2, A1 plus lambda D1, and then A2 plus mu D2. So now we've got to introduce mu as well. We've got A2 and we've got D2. Then those two lines are parallel if D1 is parallel to D2, which you might recall from our work earlier on vectors, means that D1 has to be some scalar multiple of D2. So if we imagine that visually, it means that D1 is this vector, and if D2 is just 3 times bigger, it will just be that vector, but the direction hasn't changed. So they're parallel, just different lengths. So as long as you can show D1 is equal to K D2, then they're definitely parallel. And if that doesn't work, then they're definitely not parallel. Of course, they're perpendicular. D1 is perpendicular to D2 if D1 dot D2 equals 0. The most important thing here, though, is you'll note that we're dealing with D1 and D2. We're not dealing with L1 and L2 or R1 and R2, and we've completely ignored A1 and A2. That's because in this case, we're talking about parallel and perpendicular vectors. So we actually only care about the direction. So we pull the direction vector out and we look at how those direction vectors interact with each other. So we're not worried about the initial starting point or anything like that, because as you know, this vector, I'll call this one D1 and this one D2. D1 is parallel to D2, and this same version of D1 is still parallel to D2. And in fact, if I pick up D1, I know my drawing is not perfectly accurate, and move it around the page, doesn't matter where I put it, D1 is always parallel to D2. So we only care about the direction. Okay, so let's look at example 5 now. So we've got our two vectors, or vector forms of a line, R1 and R2, and they're in terms of lambda and mu. And we first need to show that R1 is perpendicular to R2. So to do that, we start by considering the direction components. So that will be D1 dot D2 has to equal 0. And if we consider D1 and D2, we get 2 and then minus 3 dot 3 and 2. We want this to equal 0, but 2 minus 3 dot 3, 2 is equal to 2 times 3 plus negative 3 times 2, which indeed equals 0. So they are perpendicular. And then we need to determine where these lines meet. So to determine where the lines meet, I'm going to start by rewriting R1 and R2 in I and J component form. So R1 is equal to 3 plus 2 lambda I. And that's come from 3i and 2 lambda I there. And then I'm going to get 4 minus 3 lambda j. And of course, hopefully you can see that that's come from 4 and minus 3 times that lambda there, j. And R2, using the same methodology, is 4 plus 3 lambda, 3 mu, my apologies, and plus negative 1 plus 2 mu j. That's R1 and R2. And now I can equate the I components, and that gives me 3 plus 2 lambda is equal to 4 plus 3 mu. I can see this is going to get a bit out of hand here in terms of fractions, but it's not too bad. 4 minus 3 lambda equals negative 1 plus 2 mu. So there's my two equations. And I can solve those two simultaneous equations to solve for mu and lambda, and then by substituting those back in, I get a coordinate or a position where these two lines meet. So let's start by rearranging this one. I take away 3, divide by 2, and I get lambda is equal to, took away 3, so I got 1 half plus 3 over 2 mu. And over here, I get lambda is equal to negative 5 over negative 3 plus 2 over negative 3 mu. which is equal to 5/3, and then that's not even plus anymore, that's minus 2/3 mu, and now I've got lambda equals something else, which means therefore that those two things must be equal. 1/2 plus 3/2 mu has to equal 5/3 minus 2/3 mu. Oh, sorry, I've just made that a negative. It should be a plus. So now I can evaluate these. 3/2 plus 2/3 is, of course, 9/6 plus 4/6, which is 13/6 mu. 5/3 minus 1/2 is, of course, 10/6 minus 3/6, which is 7/6. And this gives us mu, use a calculator if you need, equals 7/13. And if mu equals 7/13, it means that lambda equals 1/2. Well, I'll set that the same way, shall I? Lambda equals 1/2 plus 3/2 times 7/13. And there's no simplification that works nicely there. That's 21/26. 1/2 is 13/26. This becomes 34/26. Or we can simplify that down to be 17/13. So we've got 7/13 and 17/13. And we can now use these to evaluate our position. R1 is 3 plus 2 lambda, which is 17/13. I plus 4 minus 3 lambda, which is 17/13. J, and remember, put brackets around these substitutions as well, otherwise it actually looks like 2 and 17/13. And if we evaluate those, I get 3 plus 34/13, and 3 is 39/13, and 34 plus 39 is 73/13. I, and then 4 minus 51/13, well, 4 is 52/13, so that gives me 1/13 J, and we can verify this using R2. So in R2, I've got 4 plus 3 mu I, and then plus -1 plus 2 mu J, and that gives me 4 plus 3 mu is 7/13, so it's 4 plus 21/13, and 4 is 52. 52 plus 21 is 73, so this is equal to 73/13 I, that's I. And over here I get -1 plus 2 times 7/13 J, and -1 is 13/13, and 2 times 7/13 is 14/13, so this is, of course, plus 1/13 J. And that is the same as over here, so it validates our solution for R1, just like you do with simultaneous equations. And then we have a position vector where those two coordinates meet. All the best.